Hello everyone, here we'll be discussing chapter 6.1, which is a discussion on areas between curves. There's quite a bit to discuss, but it's all really the same flavor. So here we say that the area of the region bounded by the curves y equals f of x, y equals g of x, and the two lines x equals a and x equals b, so those two vertical lines you can imagine, where f and g are continuous and f of x is bigger than or equal to g of x on the interval a to b is, so it's a mouthful, but the area is actually just the integral from a to b of f of x minus g of x. And it's not too hard to explain why this is the case. A nice picture will help demonstrate that. Notice since f of x is greater than g of x for all x values in the interval a to b, and you can think of f above g like this. Now it could possibly be equal to, so let's just imagine that it crosses f somewhere here and otherwise not. So let's imagine that this is, again, this is g. So imagine this is the x-axis, and then over here, let's say we have the y-axis. Doesn't really matter. And where they intersect, let's say, is A. And we're going, of course, from A to B. So that let's say over here, this is B. Awesome. So what we're trying to find is a formula for the area between these two curves, in between these x values, A and B. Now I've given it to you, and clearly it's the case because since f of x is, well, above g of x, the integral of f of x dx from a to b is the whole area up to the x-axis. The area in white here below the red shaded is just, well, the integral of g of x, which is the area below the curve g up to the x-axis. So notice if you take the area of f and take away the area of g of that, you're left with only the shaded region, and literally that's just the integral of f minus the integral of g, and then that really ends up just being the integral of f minus g with that one difference property of integrals, that the integral of a difference is the difference of the integrals, and of course from a to b because those are x bounds. Great. So again, f here is the top one, so think of it as top minus bottom, and as it turns out, it doesn't actually matter if this image or this region is below the x-axis or even crosses through. This result will actually always be positive, and that makes sense because again, f is always going to be bigger than g, so you're always going to have bigger minus smaller in this region, and when you take the antiderivative, the values end up still being positive because the area above is always going to be greater than the area below, even if you're below the x-axis actually. So that's kind of a little difficult to see, but if you run through a few examples, and I think we'll see one here in a moment, that will kind of explain that a little bit. So now for this example, we want to find the area of the region bounded by these two curves and this one x value. Now, the kind of best case scenario is that we have two y equals and two x equals. The two x equals will be our a and b, the two y equals will be our curves f of x and g of x. Sometimes you're only given one curve, which is kind of easy in some sense because all you need to do is find the area, of course, under that curve, which is just the integral of that function itself. So now the question is, which one is f of x and which one is g of x? So the actual answer is it doesn't really matter because since f is always going to be bigger than g of x, you can honestly just assume the first one's f of x, for instance. So imagine this is top minus bottom. If we guess wrong, then our area would be negative. Now, I know that's maybe saying a little much before actually trying it. So instead, let me do this. I'm going to actually graph these things. At least I'm going to try my best to graph them. Now, x squared minus 2 is a parabola shifted down 2 units. Something like this. Okay, 4 minus x is a line with y-intercept of 4, which is way up here, and a slope of -1. So you go down 1 over 1. So it looks something like this maybe. And look at that, the parabola and the line intersect actually in two places. They intersect over here. If you want to find out where they intersect, there's a simple value you can plug in to see that that's the case. And notice that the zeros of the parabola x squared minus 2 are just plus and minus radical 2. So this is going to be bigger than radical 2. So you can guess 2 or 3 or something like that, and then see if it works. But it could be a fraction for all we know. The actual way you find the points of intersection is, of course, by setting these equal to each other, the functions equal to each other. So if one is f of x and one is g of x, if you solve the equation f of x equals g of x, so setting the y's equal to each other, and solving for x gives you exactly where the functions intersect, where the curves intersect. So in this case, it's a quadratic, and we move everything to one side, so the zero's on the other. So I hope that wasn't too fast, but I'm adding x to the left, subtracting 4 to the left, so we get -2, -4 combined to -6. This, of course, factors as, let's see, I guess it's x minus 2 times x plus 3 equals 0. Using the zero product property, x is either equal to 2 or -3, and I know that by setting each of the factors equal to 0, because two things multiply to 0 only when one of them was 0, so either that's 0 or that's 0, and as a consequence we get these values. So positive 2 is indeed the positive value where they intersect, and the negative value where they intersect over here would be at -3. So if we were to find the area between these curves only, then the limits of integration would for sure be -3 to 3, and we know in this region the line is actually on top, so it would be this one minus that one actually. But we're not quite given this, because notice we're given this x equals 6, which is some vertical line way over here. So I actually need to redraw this a little bit. So I'm going to actually erase a lot of this work, shift my drawing over here, and then we'll continue the work. Alright, so I've obviously erased a bunch of things here, and I've shifted my drawing over here so it looks a little more accurate. And now notice what we had before was the full parabola, kind of both sides we saw where the line intersected both sides of the parabola. But we found out we don't really need that, because since we're included this, we have this vertical line x equals 6 included, we need to find the region that's bounded by these three, which ends up being this shaded region over here. Funny enough, this is actually quite a large region, as you can tell. I mean, I don't really have room to draw it, but I'll kind of show you a little bit. I just wanted to do this live in front of you all. Well, not live, but you know what I mean. So it ends up being this kind of crazy triangular looking region, but it's kind of curvy on top actually. And we can, so I guess I could shade all of it. I didn't even draw all of it because it intersects somewhere up there. So we don't really care where it intersects. All we really care is where we're going from what x value to what x value, what's on top, what's below. So now notice that the curve y equals x squared minus 2 is above. The curve y equals 4 minus x is below. So we're actually going to do this one minus this one, from this x value to that x value. Now the x value where they intersect, we found earlier with the work we did earlier, was 2. So the setup for this area will be the integral from the lower bound 2 to 6, the upper bound, of the function on top, the curve on top, which is x squared minus 2, minus the one below, which is of course 4 minus x dx. Now what you may notice is that after we distribute the negative here, what we'll end up getting is x squared minus 2 minus 4, which is -6, and then we get a plus x here actually. So I'm actually going to simplify that here, if you don't mind, as x squared plus x minus 6, which should look a little familiar to us. It's literally what we got when we solved for the limits here. So it's kind of interesting when we see that come back to us. And, right, so now we need to antiderive. Antiderivative of x squared is x cubed over 3, x cubed to the 3, I should say. Antiderivative of x is 1/2 x squared. Antiderivative of -6 is -6x. And then we evaluate this between limits 2 and 6, just like that. Great. So now, it's a little bit of calculation, but when you plug in 6, we get, let's see, that's 6 cubed, which is 216 over 3, which is actually 72. Yeah, so I'll just write 72. It's not too hard to see that. Plus, when you plug in 6 here, you get 6 squared is 36 divided by 2 is 18. Minus 6 times 6 is going to be 36. So that's me evaluating it for the upper limit. Minus evaluating for the lower limit, we'll get, let's see, 2 cubed is 8, so that's 8 over 3. There we go. Plus 1/2 2 squared. 2 squared is 4. 1/2 of that is 2, so it's plus 2. And then minus 6 times 2 is going to be 12. Awesome. So now notice here, if we add 72 and 80 and 18, we get 90. 90 minus 36 is 54. And I guess, well, you can distribute this negative, I suppose. And notice these two will combine to negative 10, but after distributing, it's positive 10. So really what we have is 54 minus 8 thirds plus 10 after the distribution. So let me just write that over here. We end up getting 64 minus 8 thirds, which, if you think about 8 thirds is 2 and 2 thirds. So if you do 64 minus 2, that's 62. But then minus 2 and 2 thirds is 61 and 1 third actually. Which if you want to write as a fraction would be, let's see, 3 times this is going to be 183, so it's going to be 184 over 3. Which I'll write like this, but I think writing it like this is kind of nice so you can see the actual value more or less of this gray area. So it's this many units squared. Now, one thing I'd like to say here is that remember that we're doing the top function minus the bottom function. Now, if we don't know, we guess like I mentioned earlier, and we did, let's say, the bottom minus top without knowing, this subtraction would be in the opposite way, so each of these terms would be negated. If you pull the negative out, what we end up getting would actually be negative of the integral we got here, so the answer in that scenario would actually be negative this. So long story short, if you don't want to figure out which one's actually on top by graphing, you can just guess, do whichever one you guess minus, or that you guess was on top minus the other one that you guess was below. And if you got it wrong, you would know because your answer would come a negative. So in that case, you just know, okay, you guessed wrong, so make it positive by taking absolute value. Awesome. So now we're going to take a look at one more example of this, and then we'll move on to the next idea. Right, so here we have two examples. Now the first one I'm going to attempt to do without graphing at all, and then afterwards we can graph to get an idea as far as what really was going on. So first off, we're not given x values, we're only given y values. So we know one's going to be on top, one's on the bottom, so we don't know our limits, that's the problem. Because the integral involves limits, so we need limits. How do we find limits? We set the y's equal to each other. Which we saw earlier actually gave us two solutions with that line of the parabola. Here we appear to have two parabolas, which may or may not intersect twice, so we'll have to see if they indeed intersect twice or not. They probably should, otherwise we wouldn't be given only two things with no x values given. But anyways, we get this. We can, of course, subtract this to the other side, this x squared that is. And we end up with 2x minus 2x squared is equal to 0. Now notice that this factors really nicely. If you pull out 2x, you get 1 minus x on the inside. And that tells us by the zero product property that either 2x is 0, meaning x would be 0, or x minus 1 is 0, meaning x would be equal to 1. So these are our limits. So now I'm going to erase this and then write the setup for the integral. All right, so we found out that the limits are 0 to 1, so the area must be the integral from 0 to 1 of the top function minus the bottom function. Now we don't know where these, we don't know which one's on top or bottom without graphing. It's hard to tell. Maybe you can kind of tell, but it's really honestly hard to do. So I'm just going to assume it's this one. So I'm going to do just first minus second. That's just my strategy. Now, of course, when you do first minus second, what you end up getting here is this minus that. And you notice these will actually combine to 2x squared, much like we had when we solved for the limits. So that's kind of nice that we see that pattern again, much like we saw in the previous example. Now, the antiderivative of each of these are, well, let's see. For this one, it's going to be x to the 2 over 2 times 2, so that's just x squared, minus 2 thirds x cubed, and then evaluate this between 0 and 1. Now, luckily, when we plug in 0, it's all 0. And when we plug in 1, we get, we get 1 minus 2 thirds, which is 1 third. So we actually guessed correctly. Look at that. If we guessed incorrectly, the answer would have been a negative value. And it makes sense because if we had guessed incorrectly, we would actually get basically this in reverse. Because it'd be x squared minus 2x, but it will be this minus that really. So x squared minus this thing, if you distribute the negative, you get x squared minus 2x, 2x squared minus 2x. And that's just the reverse of this, and you end up getting negative 1/3 in that case. Great. So now how can we graph this to show that this is indeed the case? Well, I'm going to graph these parabolas. Now the parabola y equals x squared is a pretty standard one that you should all kind of know and love. Well, the last part may not be true depending, but that's fine. And this one here, there's a negative in front of x squared, so it's a downward facing parabola. And actually you can see that if you factor an x out, this is really x times 2 minus x. meaning its x-intercepts are actually 0 and 2. So it's a downward facing parabola that passes through x equals 0 and x equals 2, and it looks something like this. So we can definitely tell that the area bounded between those two parabolas is this region right here, and it looks like the bounds are in between 0 and 1, and we indeed see that 1 works. Of course, if you plug in 1, you'll get the same value for both. 1 squared is 1, 2 times 1 minus 1 squared is also 1. Perfect. So yeah, so this area we actually found, and the area is just 1/3. Fantastic. And again, if we guessed incorrectly, then we would just say it's the absolute value of that, which is positive 1/3. Now for this next example, like I said, we wanted to move on to a new idea. We're going to see that new idea through this kind of. I would like to try this similar to how we did the previous problem. It's not actually going to work, and let's kind of see why. So with the previous idea, it would be the area equals the integral from, we already have our bounds, so it's from 0 to pi over 2, of top minus bottom, so let's just guess sine of x minus cosine of x. Perfect. Then we take the antiderivatives. Antiderivative of sine is negative cosine. Antiderivative of cosine is positive sine, but it's negative already, so it's going to be negative sine. Right? And then evaluate this between our limits 0 and pi over 2. Now when you plug in pi over 2, cosine 0, sine is 1. So we're going to get 0 minus 1 for the first evaluation. Minus, when you plug in 0, cosine of 0 is 1. So we're going to get, let's see, there's going to be negative, yeah. So cosine of 0 is 1, so it's going to be negative 1, and then minus sine of 0 is 0. So this really is negative 1 minus negative 1, which is negative 1 plus 1, which is 0. That doesn't sound great, because that means the area between the curves is 0. So what exactly does that mean? I mean, clearly sine of x and cosine of x have regions, like there's no spot where you would have a 0 area. Basically what this kind of means is that there was a negative area involved. But how can there be a negative area involved when I said the area will always be positive? Essentially what's happening here is that one of the functions is in top in one region, so you'll have one minus the other, but then on the bottom in another region in between these two. In other words, there is an intersection point between these two limits that are given to us. So in reality, this method kind of works, but we still have to take the first step, which is finding intersection points. Now, if we had done that ahead of time, we would have seen that sine of x is equal to cosine of x, of course, when x is equal to pi over 4. Of course, there are other values where sine is equal to cosine, but the only values in between 0 and pi over 2 are indeed pi over 4. Notice sine of pi over 4 and cosine of pi over 4 are both the same radical 2 over 2 value. So what this tells us is that there's actually an intersection point. So it's hard to visualize what's going on, but really we have a middleman hidden point here. So to find the area between the two curves, we need to find the area between this guy and the middle one, and then the middle one, and then the last one. So now I'm going to try to, erase this and set that up, and then we'll go from there. Afterwards, we'll graph to hopefully get a better handle on what really happened from a graphing perspective. All right, so I've obviously erased some things, and I've included that we have this kind of hidden middle term, or middle intersection point of these two functions. So one's on top in one scenario, but remember that this is, we always want to go from smaller to bigger. So if that's the case, we must go in order. So it's going to go from 0 to pi over 4 first. Of 1 minus the other, so we'll guess here, that's fine. Perfect. So that's one of the areas, but then we have to go from the middle intersection point to the last limit. So pi over 4 to pi over 2 now. Now it's not going to be the same integrand, because here we assume sine was on top and cosine was on bottom, but after intersecting, if sine was on top and cosine was on the bottom, let's say, after intersecting now it'll be the opposite case. So now sine will be on top, now cosine will be on top and sine will be on the bottom. So this will be cosine minus sine. And again, this is assuming that sine is indeed on top in the first region. So we're still kind of guessing, and we have that idea behind picking basically which one's on top, just a guess. But we'll have an idea that these two should both be either both positive or both negative. So let's see. So we know the antiderivative, of course, will be, I'm trying to see if there's anything else we can do. I guess it's okay. So we know again that the antiderivative of sine is negative cosine, antiderivative of negative cosine is negative sine. We're going to evaluate this between our limits 0 and pi over 4. When you plug in pi over 4, they're both radical 2 over 2. So it's a negative radical 2 over 2 minus radical 2 over 2, which I'll write actually. I wanted to say that's just negative radical 2, but we'll get to that point in a moment. Plugging in 0 gives us negative 1 minus 0. And then plus, very similarly, antiderivative of cosine is sine. Antiderivative of negative sine is, well, positive cosine. Evaluate between pi over 4 and pi over 2. We have that guy in brackets plus this new one in brackets, which will be, let's see, plugging in pi over 2 gives you sine of pi over 2 is 1, plus cosine of pi over 2 is 0. So that's the first evaluation. Minus the second evaluation is, well, again, they're both the same pi over 4, which is radical 2 over 2. And notice radical 2 over 2 plus radical 2 over 2, again, is just 2 times radical 2 over 2. The 2 in the bottom cancels. So you end up just getting radical 2. So once all is said and done, what we end up getting here is negative radical 2 plus 1. Here, we end up getting 1 minus radical 2. Okay, so like I said, they're either both positive or they're both negative. They're actually the same, notice. We have a negative radical 2 and we have a positive 1. So when we combine these, we just get 2 times that quantity. So they're both the same area as it turns out. And we'll see that after graphing, I think. And if we combine them, we get 2 minus 2 radical 2. And this is clearly, at least to me, it's clearly negative because radical 2 is 1.4, which is bigger than 1. So 2 times something bigger than 1 is bigger than 2. And 2 minus something bigger than 2 is negative. So this is not actually the right answer. So instead we have to take the absolute value of this to be the right answer. And that really just boils down to negating it. So the absolute value of something, of a difference that's negative, will be the difference in the opposite order. So this will indeed be the answer. And again, the reason why I know that swapping it will be okay is because that's what we really should have done. So we guessed incorrectly actually. Sine was not on top here, sine was on the bottom. And I'll graph this pretty quickly over here. So notice we only need from 0 to pi over 2. That's fine. So now as far as sine is concerned, sine looks something like this between 0 and pi over 2, because then it goes like that, hits pi and then goes back up. Cosine will start at y equals 1. Let me do that again, sorry. It's a little better. So cosine starts at 1 and then goes down like this. Okay, so it's not super obvious that these are actually the same, but after looking at it for a bit, you can kind of see that these areas are actually the same. And they're each radical 2 minus 1. Where they intersect, so there's some symmetry here, but where they intersect for sure is at pi over 4, as we saw previously. So notice, and maybe I should label these, this on top is y equals cosine, where this one now on the bottom, which I guess is on the top over here, is y equals sine. So notice, from 0 to pi over 4, which one's on top? Cosine. Sine's below, because sine is this curve. So we're going to have cosine minus sine. We got that wrong, so that means the answer should be negative that, which is radical 2 minus 1. Similarly, from pi over 4 to pi over 2, sine is on top, cosine's on the bottom. We also guessed that one wrong. But we knew, of course, since we passed an intersection point, whichever one's on top or bottom, those roles actually reverse once we pass that intersection point. So that's what gave us the impression that we have to do the subtraction the other way around, which was the right idea, but again, since we had this incorrect, then they would both be incorrect. But anyways, we still got the answer non-graphically, which is pretty impressive. But Yeah, it was a little weird because we got a false answer and we knew it was false because area between curves should never be 0. Not only that, it's a little concerning because without graphing, you can't really tell if this always happens. Unless you say your y's equal to each other no matter what, even if you are given limits, that way you can kind of tell, okay, there's an intersection point, and then you can start to kind of visualize it, but at that point, might as well just graph. So this, I think, illustrates the power of graphing when it comes to finding the area between curves. Now, the last thing we're going to be taking a look at is, well, another example, but it'll be one where we kind of have to view things sideways, if you will. And there's a really nice way of visualizing this as far as swapping variables. We'll take a look right now and we'll see what that's all about. Right, so I think this will actually be our last example here, and this one's kind of interesting. So it is asking us to actually to sketch the region enclosed by the given curves and then find its area. So we have no choice but to graph because it's asking us to. So now to graph x equals y cubed, sorry, not y cubed, but y to the fourth. Well, y equals x to the fourth looks kind of like a parabola, but it kind of has like a wider jaw. So the graph x equals y to the fourth will be kind of a sideways image of that. So I'm going to label this as x equals y to the fourth. Anytime, by the way, you're graphing something that has the kind of opposite feel to it, where instead of y in terms of x, it's x in terms of y, just kind of tilt your head and pretend your x-axis is your y-axis, and vice versa. So that's kind of what's going on. In fact, if you tilt your head, this looks, well, it will look like y equals x to the fourth. Great. So now this one's a little challenging to explain what the graph will look like. I know radical x will look kind of like what we have here for the top part, but since the x is negative in the inside, it's actually flipped around. And this 2 kind of tells me that it has an x-intercept radical 2 because when x is 0, the y value will be, actually, I'm sorry, when, let me see. Yeah, so here we go. So when x, there we go. So when y is 0, the x value has to be 2 because 2 minus 2 will give you 0. So that's kind of a weird way of looking at it, but we end up getting this kind of image here that will look something like that. Now, if you don't quite like that idea I explained, there's another way of doing it, which we'll kind of have to do anyways, kind of. And that is actually solve for x in terms of y. So if we square both sides, we get this. And then if we solve for x by adding to the other side and simultaneously subtracting y squared, which is sometimes known as a difference swap, you end up getting this, kind of swapping the two parts of the difference. And yeah, this is actually, if you think about, if you think of it as y equals 2 minus x squared, negative x squared is a downward facing parabola, but when you add 2 to it, you're shifting it up 2 units. So again, if you kind of tilt your head, you get this kind of parabola, but it's only the positive side part of it because it came from a positive radical. So if you were to graph this, it would actually be the completed parabola like that, which is kind of nice to look at. But we're not looking at the dotted part, we're only looking at this. I don't know if the dots came out on screen nicely, but up close it kind of. So this is supposed to be dotted. But anyways, we're not considering that, we're just considering the upper half here. In other words, we're looking at this region. Also notice y equals 0 is just the x-axis. So this is y equals 0. And you can label this as x-axis if you'd like. And in fact, yeah, that's a kind of reminder to us. Y equals 0 is the x-axis, and much like that, x equals 0 is actually the y-axis. Great. So now, the only issue is you kind of have to figure out where they intersect. And it's not difficult to do. In fact, you can set their x's equal to each other and solve for y. But that would be solving for the y value. To solve for the x value, you would have to, I guess we can substitute kind of. So if you solve for y here, which kind of it already is solved, there's like so many ways of doing it, which is kind of funny. It looks like it's going to be 1. If x equals 1 corresponds to the same y value, we can check that. So when x is 1, what must y be? Well, if x is 1, y must also be 1, because if you subtract 2, you get negative 1. Negative 1 equals negative y squared, means that y would equal positive 1 or negative 1, but that would be the dotted case. So yeah, it's definitely positive 1. And here notice, When x is equal to 1, y must also be positive or negative 1 yet again. So that makes sense. They intersect here. So that's when x is equal to 1. So what this tells us is we kind of have scenarios similar to what we had before, where we have this intersection point. The issue is that it's not really like top and bottom, it's more like which one we're using. So here we'll be using y equals, y to the 4th equals x. Here we'll be using this curve here, y equals radical 2 minus x. Now in order to actually take the integral, we have to write things in terms of, in terms of x. So we could actually write this, if you want, as y is equal to the 4th root of x. But that of course corresponds to the positive root, not the negative one. So now this becomes dotted, which is kind of funny. But we don't really care about that part anyways, so we can kind of throw it away regardless. So we'll be going, so the area will have this set up then. It'll be the integral from 0 to 1, okay, of the first guy, which is the 4th root of x, which is x to the 1/4 dx, plus the integral from 1 to 0 of the second one, which is radical 2 minus x, which will require a u substitution. It's not too bad. Dx. Alright, so I'm actually not going to do this though. So you can knock yourself out, try this, it'll be a lot of fun. Instead, I want to do something a little different. I'm going to actually view this sideways. It's better to view this sideways in this case because this has x in terms of y screaming out to me. I mean, you can kind of see it when we're looking at it at first. We're constantly translating between x in terms of y in terms of x. But in reality, if you kind of tilt your head, you're really going from y equals 0 to y equals 1. We've already established that this point has a y value of 1. So really we're going from y equals 0 to y equals 1. And this curve here is on top, where this curve is on bottom. So it's really best to kind of flip the image a little bit. So in fact, you know what, let me erase this. And again, you can try this on your own if you like, but I'm not going to do it that way. Instead, what I'm going to do is I'm going to try to flip the image of it to view what's going on. So our first quadrant is still the first quadrant here, but now we're treating this as our y-axis and this is our x-axis. Again, that's to kind of flip the image. And below we'll have x equals y to the 4th, which will look like this. And above, we will have this curve, which is x equals 2 minus y squared. So clearly it's much easier to see it this way because it's kind of like exactly what we saw at the very beginning, at least what we're kind of used to from that point, or in that regard anyways. So in fact, one way of going about this is just swapping all x's and y's, and then we'll kind of clearly see that we're going from x equals 0 to x equals 1. But in reality, since it was originally with x and y's the other way around, we're really going from y equals 0 to y equals 1. So I'm going to keep it like that. It's kind of hard for me to visualize it sideways like this. So I very often like showing people that if you just swap x and y axes, you end up getting this image. Just make sure that your positive or negative directions are still sorted. So it's not just staring at it sideways, but it's also kind of flipping the image or making sure this is positive and that's positive. So we end up getting this. Okay, great. So now that we have that settled, the area here will actually be the integral from y equals 0 to y equals 1 of the top one, 2 minus y squared, minus the bottom one, y to the 4th dy. Much more manageable. No u substitution actually required. So here, the antiderivative of each term will be 2y, negative 1/3 y to the 3rd, negative 1/5 y to the 5th, evaluated between 0 and 1. When you plug in 0, of course it's all 0 because they're just powers of the variable y. So that goes away. When you plug in 1, you literally just get the coefficients added to each other, which is 2 minus 1/3 minus 1/5. Which of course the negatives actually combine to, let's see, that's going to be 5 plus 3 all over 15. So that's 8 over 15. So it's 2 minus 8/15, which if you think of 2 as 30 over 15, 30 minus 8 will be 22 over 15. Just thinking of it like that as one fraction. Awesome. And if you want to write this, of course, as a mixed number, it's 1 and 7/15, just to give an idea of what the actual value of this area is, which sounds a little, yeah, it sounds correct actually, because if you kind of look at these kind of unit squares, we get the impression that each of these a little more than half. So if you have a little more than half added to a little more than half, then you get something that's bigger than 1. And this is a little bigger than 1. It's 1 and 7/15. It's actually, yeah, it's a little less than halfway between 1 and 2. So it's a little less than 1.5 basically. But anyways, that's all I'm going to say as far as that goes. So we saw a few things. We saw area between curves, so just kind of in general what that was. And then we saw that there are some situations where you may have intersections where top and bottom swap. And then we also saw scenarios where you may have to view things from a different perspective because we have x in terms of y instead of y in terms of x. We usually do. Awesome. So that's really all 6.1 is. And in the next video for 6.2 and even for 6.3, we will be looking at something similar to this, but only instead of areas, it will involve volumes. So what we'll be doing in that case is we'll actually be taking a look at these kind of regions and not finding their areas, but rotating those regions about a line, getting a generated three-dimensional solid, and actually finding the volume of that solid, which is kind of interesting and a little mind-blowing in some sense. So I'll see you in the video for that. It's going to be a lot of fun. Really hope you enjoyed this. Thanks for watching, and I'll see you then.